The universe whispers. Not in words we understand, but in subtle tremors, vibrations that travel across the vast expanse of space-time. These are not sound waves, but something far more profound: gravitational waves. They are ripples in the very fabric of the universe, generated by the most cataclysmic events imaginable. Colliding black holes, exploding stars, the Big Bang itself. For centuries, we were deaf to these whispers. We gazed at the stars, capturing their light, but remained oblivious to the symphony of gravitational waves passing through us. Then, a century ago, Albert Einstein, in his theory of general relativity, predicted the existence of these waves. He envisioned gravity not as a force, but as a curvature of space-time, a cosmic dance floor where matter and energy dictated the steps. Einstein's theory revolutionized our understanding of gravity. It explained why objects fall to the Earth, why planets orbit the Sun, and why light itself bends in the presence of massive objects. But his theory also made a startling prediction that accelerating masses would create ripples in space-time, propagating outwards at the speed of light. These ripples, he argued, were gravitational waves. For decades, Einstein's prediction remained just that, a prediction. The waves were too faint, too elusive to detect, but scientists never gave up hope. They devised ingenious methods, built ever more sensitive instruments, and in 2015, the universe finally whispered loud enough for us to hear. Imagine a still pond. Toss a pebble into it, and you see ripples spreading outwards, disturbing the smooth surface. Gravitational waves are similar, but instead of water, they ripple through space-time itself. The pebbles in this cosmic pond are some of the most energetic events in the universe. Colliding black holes, merging neutron stars, or even the Big Bang itself. These events release tremendous amounts of energy, shaking the very fabric of space-time. These shakes, these ripples, are what we call gravitational waves. They travel outwards at the speed of light, carrying with them information about the cataclysmic events that birthed them. Einstein's theory of general relativity provides the framework for understanding these waves. It tells us that mass warps space-time, creating the effect we experience as gravity. When massive objects accelerate, they create disturbances in this warp, propagating outward like ripples on a pond. The more massive the object and the stronger the acceleration, the larger the ripples. However, these ripples are incredibly faint. Even the most powerful events in the universe create gravitational waves that stretch and squeeze space-time by an infinitesimal amount. Detecting them requires instruments of extraordinary sensitivity, capable of measuring distortions smaller than the width of an atomic nucleus. Imagine two black holes locked in a deadly embrace. They circle each other, their immense gravity pulling them closer and closer. As they spiral inwards, their dance becomes faster, more frenzied. They lose energy, radiating it away in the form of gravitational waves. These waves carry the signature of their cosmic tango, a fingerprint of their mass, their spin, and their final cataclysmic merger. Einstein's theory of general relativity predicts this dance in exquisite detail. It tells us how the black hole's motion distorts space-time, creating the ripples we call gravitational waves. It predicts the frequency of these waves, their amplitude, and how they evolve as the black holes spiral closer. This theoretical framework is crucial for interpreting the signals we receive from gravitational wave detectors. By comparing the observed signals to Einstein's predictions, we can learn about the properties of the objects that generated them. We can determine their masses, their spins, and even the distance to their cosmic dance floor. This is the power of gravitational wave astronomy. It allows us to see the universe in a completely new way, not through light, but through the ripples of gravity itself. It opens a window into the most extreme environments in the cosmos, where gravity reigns supreme and the laws of physics are pushed to their limits. Section 4. Catching the waves, LIGO and Virgo. For decades, detecting gravitational waves seemed like an impossible dream. The waves were simply too faint, their effects on space-time too minuscule to measure. But scientists persevered, driven by the promise of a new window into the universe. Their efforts culminated in the Laser Interferometer Gravitational Wave Observatory, or LIGO, a marvel of engineering and precision. LIGO consists of two identical detectors, located thousands of kilometers apart. Each detector uses laser beams to measure tiny changes in the distance between mirrors, suspended at the ends of two perpendicular arms. When a gravitational wave passes through the Earth, it stretches and squeezes space-time, causing the mirrors to move ever so slightly. These movements are incredibly small, far smaller than the width of an atomic nucleus. Yet LIGO is sensitive enough to detect them. By comparing the signals from the two detectors, scientists can filter out noise and confirm the detection of a gravitational wave. In 2015, LIGO achieved the impossible. It detected the first gravitational waves emanating from the merger of two black holes over 1 billion light-years away. This historic discovery confirmed Einstein's century-old prediction and ushered in a new era of gravitational wave astronomy. Section 5. A new symphony of the universe. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events. They have listened to the whispers of merging black holes, the chirps of colliding neutron stars, and even the faint hum of the early universe. Each detection adds a new note to the cosmic symphony, revealing the secrets of the most energetic events in the cosmos. Gravitational waves provide a unique perspective on the universe. They allow us to study objects and phenomena that are invisible to traditional telescopes. Black holes, for example, emit no light, but their gravitational waves speak volumes about their properties and behavior. Neutron stars, the collapsed remnants of massive stars, are another prime target for gravitational wave astronomy. When they collide, they create a spectacular firework display of light and gravitational waves. Studying these waves allows us to probe the extreme physics of these objects, where matter is compressed to unimaginable densities. Gravitational waves also offer a glimpse into the earliest moments of the universe. They carry information about the Big Bang, the primordial explosion that created everything we see around us. By studying these waves, we may one day unravel the mysteries of the universe's birth. Section 6. The future of gravitational wave astronomy. The field of gravitational wave astronomy is still in its infancy, but its future is bright. New detectors are being built, promising even greater sensitivity and the ability to detect fainter signals from more distant sources. These detectors will open new avenues for exploration, allowing us to study the universe in unprecedented detail. One exciting prospect is the detection of gravitational waves from the Big Bang itself. These waves, known as primordial gravitational waves, would carry information about the universe's earliest moments, providing invaluable insights into its origin and evolution. Another promising area of research is the study of gravitational waves from supernovae, the explosive deaths of massive stars. These events are crucial for understanding how heavy elements are created and distributed throughout the universe. Gravitational wave astronomy is revolutionizing our understanding of the cosmos. It provides a new way of seeing the universe, complementing traditional astronomy and revealing secrets that would otherwise remain hidden. As we continue to listen to the whispers of gravity, we are sure to make groundbreaking discoveries that will reshape our understanding of the universe and our place within it.